Hello, I'm Dave Thomas. I don't know if you've noticed, but for the last 10 years or so, our computers have not been getting any faster in terms of clock speed. I mean, we've been able to do more with them, but the actual clock speed itself seems capped at 2, 3, maybe 3.5 gigahertz. So what's going on? Well, I did some poking around to find out, and what I found was really interesting, so I thought I'd share it. And I think it also helps me understand why the future has to be parallel, and as a result, I think also has to be functional. But let's have a look to see exactly what's going on and what's driving that trend. Starts with this man. I'm sure you've heard of Moore's Law. This is Gordon Moore. He used to run Intel. And he was doing a back of an envelope calculation based on historical data. And he decided that for Intel, the number of gates they could economically put on a slice of silicon was going to double roughly every year. And then after a while, he revised that and said, actually, no, it's about 2 years. And then one of his engineers looked at that and said, 18 months is probably a better bet. But you know what? It doesn't matter. If you're doubling every year, every 2 years, you're still looking at a phenomenal rate of growth. And so if you're going to double every 2 years or every 18 months, right, what does that mean in practice? Well, let's have a look at the number of transistors that are on a slice of silicon, a typical slice of silicon, over the last 50 or so years. It looks like an absolutely straight line, and it pretty much is. But if you look at the y-axis, you'll see it's logarithmic, which means that actually the number of gates that we're putting on a piece of silicon is actually going up exponentially, just as Moore's law would assume. But if we look at the clock frequencies of those processors, we see a very different trend. Here we see that the clock speeds were also going up pretty much exponentially until around about the year 2000. And then they started tailing off. And now we're seeing almost no growth at all in clock speed. So how come our computers are getting faster? Well, it's not because they're getting clocked faster, it's because they're getting more cores in them, more independent processing units on a chip. So if you have a 4-core machine, you can do, in theory, 4 things in parallel. But the question is, why? Why are we having to go to cores and not just keep bumping the clock frequency up? And it turns out it's to do with a empirical law that says that the power that's consumed by a circuit is proportional to the cube of the clock speed. Now, we can actually say that it definitely has to be the square of the clock speed, and that's because each of the gates in our processors acts like a tiny little capacitor, and it switches from one state to the next when it reaches a certain threshold voltage. Now, if you want a capacitor to change quickly, then really the only way to do it is to reduce its capacitance or to increase the voltage you apply across it. So to get our computers to switch faster, we're increasing the internal voltage, and power goes up as the square of the voltage. But there's more to it than that, and that's why we have this cube. First of all, as the gates get smaller, we start to get leakage between the gates, and so that eats up power. And there's another interesting effect. As our gates are switched faster, then there are times when 2 opposing gates are both in the process of switching. And that acts as a little short circuit. The faster your clock frequency, the more frequently that happens. And so, as a result, we're looking at this kind of cubic relationship. Now, whenever you get a cubic relationship, that's kind of scary. It starts off nice and small, but as time goes on, as the clock speed increases, our power gets really out of hand. If you double the clock speed, our power is going to go up by a factor of 8. If you triple it, it goes up by a factor of 27. That's a lot. Let's get back to kind of reasonable numbers, though. Let's say you're overclocking your processor, and you want to increase the clock speed by about 10%. Well, in that case, our power is going to go up 1.1 cubed to 1.33%. So we have a 33% increase in the power consumed, which also means we have a 33% increase in the heat, because that's where all that power is going in the end. Now, if you've ever done any gaming and you've maybe built your own machine and tried to overclock it, then you'll know that heat is your biggest enemy. If you get it wrong, then this is what happens to your processor. But it's not just your processor that is at risk. All that heat we're generating is going somewhere. They reckon that in the US, roughly 2% of the energy used by the entire country is used by data centers, which is basically our processors burning up electrons. And that heat's going out into the environment, and it's obviously contributing to issues with the global climate change. So it'd be nice to try to reduce this. And to reduce that, we go back to our formula that power is proportional to the cube of the clock frequency. We take a processor, but this time rather than increasing the clock frequency, we're going to decrease the clock frequency. Let's say we take it down to 70% of what it was previously. Now, what does that do to the power consumption? Well, it's 0.7 cubed, so it goes down to roughly a third of what it was. Now, what we can do is take 3 of those processors running at 70% of the original speed. Those 3 processors between them are going to do 210% of the processing of just one processor. That's 3 times 70%. And the power they're going to consume is only the same as the original processor that we took. So what we've done is by slowing a processor down and replicating it another 2 times, we actually end up using exactly the same power and getting 2 times the compute capacity. That's magical. And that is why we're going to see more and more multi-core computers with larger and larger numbers of cores. That's all very well, though, but there's a problem. If you're to make use of this, you actually have to write programs that can use all of those cores at the same time. If your magic program only runs on one of the 16 cores in the machine, then it's going to run a 16th as fast as it could run, and your users are going to complain. But writing those kind of programs is tricky. So that's why I say that the future of software is parallel and concurrent. I don't think we have any choice. However, it's hard to write parallel code. If you've ever tried it in Java or Ruby, you'll know that you're constantly worrying about deadlocks and semaphores and critical sections and all sorts of stuff like that. It needn't be that way, though. And that's why I'm really excited about the Elixir programming language, which makes it really straightforward to write reliable, concurrent code that scales remarkably. I'm also really excited by the Phoenix framework. There's a kind of misconception out there that Phoenix is a web framework. It isn't really. Phoenix is a switching framework, which allows you to basically take data in at a remarkable rate, high concurrency, and process it and then send it back out somewhere else. So between the two of them, I think we actually have the future pretty well covered. And that's why I'm going to be making more and more videos about Elixir, about Phoenix, and about how to write in the parallel concurrent future. See you there.